Hi, welcome back to the Alkene Edition playlist in organic chemistry. I'm Kevin Tokoph. Please like the video and subscribe to the channel if you like it. In this video, we're going to go over one of the types of addition reactions in organic chemistry, and that's called halohydrin formation. So what exactly is a halohydrin? Well, a halohydrin is a molecule that has both a halogen in it and a hydroxyl group. Hydro or hydrin usually implies something like an alcohol or water, and so that we're going to use water to add the hydroxyl group, and the halo just means we're also going to use a halogen to add either bromine or chlorine to the molecule. This reaction, at least mechanistic wise, is almost identical to what we saw in the last video, which was just simple straight halogenation. Okay, in fact, it's going to involve a lot of the same intermediates, but there's a big difference. Okay, if we were just doing simple halogenation right here, you would just see chlorine. But actually, if we want to form a halohydrin, we also need to put water as one of the ingredients or the reagents that we're going to use to do this. Okay, now this is just like halogenation in the sense that we can't use diatomic fluorine or diatomic iodine. We can't use either one of those. Okay. We can only use chlorine or bromine, and that's just because of the formation of the intermediate. It's too slow with iodine and way too explosive reactive with fluorine. Okay, so what is in general what the reaction does? Well, it's going to add one hydroxyl group and one chlorine in the case of chlorohydrin formation, and in the case of bromohydrin formation, it's going to add one bromine and one hydroxyl group. Very similar. But the question is, where does the hydroxyl group add and where does the halogen add? Well, the rule for this, and we'll explore why that is the hydroxyl group always adds to the more substituted carbon, and the halogen adds to the less substituted one. Okay, and there's a reason why it does that, and we'll look at that in just a minute. Okay, notice on this alkene, this carbon obviously is more substituted. Even though it has one substituent, the one on the right has zero. It only has hydrogens. So that's why the alcohol adds to the left carbon. Okay. We're going to look at another example. Let's look at this one below it. Okay. Again, the left carbon has two substituents and it's more substituted. The right one has only one, and again, it's the least substituted. So we would expect the alcohol to add to the more substituted, the left side, and then the chlorine or the halogen, whichever one we're using, in this case it is chlorine, adds to the right side. Okay? So here's kind of the general rule of thumb with this type of reaction. Okay? Now obviously all the stereochemistry isn't indicated here, but there is a point I want to drive home. When we looked back at halogenation of an alkene, remember it was what we termed an anti-addition. Was an anti-addition. Well, because the mechanism is almost the same for halohydrin formation, it's also an anti-addition, which just means that the two groups are going to be added on opposite sides of the double bond, meaning that if the hydroxyl group is on a wedge, then the halogen has to be on a dash. Likewise, in this one, if the hydroxyl group is on a dash, then the halogen has to be on a wedge, and that's just the general rule of thumb with this reaction. Okay? And so, again, you're using a halogen like chlorine and water, okay, and you get this. Likewise, I can do the same thing basically with bromohybrid formation if I use bromine and water, okay. Again, I'm just showing you the general reaction, so notice we add bromine and a hydroxyl across the double bond. Remember, again, notice that the left carbon is more substituted, therefore, I expect the alcohol to add there. The right side is less substituted, only one substituent, so I expect the bromine to add there. And it does in both of these cases. Now, one of the things, because it is an anti-addition, you actually get a couple products. You get what are referred to as enantiomers. Okay? If there's already another chiral center, then you get diastereomers. The whole point here is that when you draw the products, you should expect enantiomers. Okay, so hopefully that makes sense. You see the hydroxyl added to the more substituted, the bromide added to the least substituted. Okay, we're going to take a quick look at the mechanism. Okay, it's going to be very similar to what we saw before, and so then we'll do a few practice problems with it. Okay, so I'm going to do the exact same problem I did in the mechanism I did in the last one, same molecule, so you'll probably hear a lot of repeats in this, but except our nucleophile is no longer going to be bromine, it's going to be water. Okay, so here's my cyclopentene that I showed you in the previous video. Now, again, what I'm going to do is I'm going to imagine drawing an axis right through here, and I'm going to just, even though there's technically sp3 carbons here, I'm going to more or less view this as just being flat on the screen. So I'm going to take this and rotate it about 90 degrees so that I'm sort of looking at this cyclopentene from the side. And actually, one thing I neglected is there's actually a methyl group I have there, and the reason I do that is just so we have one side more substituted than the other, but it's going to be otherwise identical. Okay, again, I have this molecular bromine. I'm using bromine as the example again. And remember, if you need more detail on this, certainly go back to the previous video. I'm going to sort of gloss over it here. But remember, bromine or molecular bromine, okay, two identical atoms in a symmetric bond. Okay, again, remember, there's some lone pairs on each of these. Okay, now remember, every atom of any kind has some electronegativity that's given for it. So this bromine is going to pull some of the electron density of the other one towards it. And then this bromine on the left is going to pull some from the right towards it. Okay? But here's the idea. It's a linear molecule and both atoms are the same. So both of these dipole moments cancel to have zero net dipole. So ordinarily, if I were to take bromine and I were to basically take it out into the middle of space, a vacuum where there's nothing acting on it, it would be perfectly symmetrically nonpolar. Okay, but there's this concept called polarization, where if I were to take some molecule and I were to put it in very close proximity to another molecule, then the electron cloud that surrounds each of these atoms, the electron cloud can get distorted, okay? And the other thing to remember also, remember, this is a pi bond, okay? So there are some p orbitals here that are regions of high electron density, okay? And so as regions of high electron density, these orbitals, which have electrons, are interacting with the red bromine, the proximal one, as it approaches the molecule. And sort of what it's doing is these orbitals are pushing the electron density towards the blue bromine atom. Okay? What that does is because the blue bromine atom is therefore receiving electron density, it gets partial negative charge. The other one therefore gets a partial positive because the red one's losing electron density. And because it has a partial positive, when it's in close proximity to this molecule, it becomes electrophilic enough to where, and I'll do the mechanism now, the pi bond here can attack that bromine. Okay, now remember, this bromine also has some lone pairs on it, and so when the bromine gets attacked, the blue bromine leaves as the leaving group, but one of these lone pairs is going to come over here and attack the left orbital, and what that effectively does is makes a bromonium intermediate. Okay, now here's the thing about the bromonium intermediate. Okay, it's sort of like an epoxide. If you have any exposure to epoxides, they're three-membered rings like this, okay, where two of the atoms are carbons and the other one's an oxygen. It's a triangle, basically. But the whole point of this is, remember back to cycloalkanes, and we talked about six-membered rings being the most stable, lowest energy. You can go to seven-membered and five-membered, and they're still pretty stable. But you start going down to four-membered ring and a three-membered ring, regardless of what the other atoms are, it's very unstable and it's very reactive. Well, epoxides are no exception. They're very reactive, except this isn't an epoxide with an oxygen. It's a bromonium with a bromine, and that's very unstable. So what's going to happen is water can attack one of these carbons. The question is, which one is it going to attack? Will it attack effectively the least substituted or the most substituted? And the thing to remember is that, remember this effect that carbon atoms have. So this carbon and this carbon and this carbon, they have this process, or not this process, but this property called hyperconjugation, meaning they're able to donate electron density into certain orbitals. Well, This carbon right here, the right one, is less substituted. So that means it would have less of a capacity for hyperconjugation. This one right here has a lot more, if I can draw, has a lot more capacity for hyperconjugation. Meaning that if electron density is being donated towards this atom, it's able to develop a much higher partial positive charge because that partial positive charge is stabilized by hyperconjugation from 3 carbon atoms versus 2 for this one. And that makes it sufficiently electrophilic enough to where water can attack it, causing this bond to break. Okay? Now what you get is you get water here, a water group that's on the bottom, and bromine kind of swings over and is on the top. And notice that is anti. They're anti to each other. They're on opposite sides of this bond right there. Okay? And then just another sort of step we just have to include is the final proton transfer, where water is going to come here and just neutralize that to make the alcohol as shown right there. But the whole point is I added water, or a hydroxyl group, to the more substituted side and the bromines on the less substituted side. Okay. Now we mentioned that you can get a pair of enantiomers or diastereomers. Let's see how that happens. And the best way to show that is basically instead of the bromonium forming on the top of this ring, what if I were to show it actually forming on the bottom? Okay, well, the same thing's going to apply. This carbon right here has a much higher partial positive charge, right? Because it has hyperconjugation from this atom, from this atom, from that, versus only 2 from this carbon. Okay, so it has much more hyperconjugation to it, therefore it can develop a much higher partial positive charge. Okay, because there's electron density from these carbons coming to it. Therefore, water can then attack that carbon being the most substituted position. And then this is going to sort of swing over there. Okay? And that's where you see this bromine over here and the water group up here. And then just like in the case of, the other mechanism from the other perspective, we have to draw water doing the final proton transfer and neutralizing this group to make the alcohol. And again, anti-addition. Notice that the alcohol group is on opposite side of this bond as the bromine, and that's what we expect. The other thing also is remember that alcohol goes to the most substituted side, the halogen goes to the least substituted. If I were to instead of this being bromine, if I just done chlorine, then anywhere you see a Br, you just put Cl. Okay, it would be exactly the same mechanism, it would be identical. Okay, so if you watched the previous video on halogenation, hopefully you have a little more of an intuitive sense there. But actually, let's do the most important thing here, which is practice predicting products. That's what they're probably going to expect you, get a drink, to be able to do on the exam. All right, so what's my technique for doing this? Normally something that's not really taught, but it works every time for these type of reactions, alkene additions that is. And so what I would like to do is tell you, if you're not familiar with this, go back and watch this and then go back and watch the video where I explain all this in a separate video. But what you do for this technique is you take the double bond, you just draw a dotted line through it. Okay? What I'm going to do is I'm going to just pick, and it doesn't matter which side you do because you'll get the right answer every time. I'm just going to pick one of these sides of the dotted line to remain in the plane or the same. So I'm going to pick the bottom this time. I change it up a lot. Remain the same or remain in the plane. What that means is for the product, I'm just going to redraw everything as is. Also, it might help to remember there's a hydrogen right there. Okay. Notice when I say it's in the plane, okay, that just means that it's not on a wedge or a dash. It's just a solid normal line that you see in the plane of the screen. When I did halogenation, I could just sort of add bromines, right? But I have to be careful here because remember, the more substituted side gets an OH group. So that's the left side. So I'm just going to put OH here on a wedge, right? Right side is less substituted. It only has one substituent. So that means I'm going to put the bromine there. But it's anti-addition, so that means I have to put it on a dash. Okay, and then everything else I'm just going to sort of fill in. This is the sort of methyl group that remained there. So it obviously therefore has to be on a dash because this is a wedge and this is in the plane. This hydrogen right here has to be on a wedge because the bromine is on a dash. Okay, and that's how you go about predicting that product. But remember, I can attack from the other side and get, basically, in this case, it would be an enantiomer. Okay, so I'm going to, again, keep everything on the bottom. I'm going to cause that to remain the same, and I'm going to draw it as such, like that. Again, the position of the OH group isn't going to change. It's just its orientation will. So now it was on a wedge here. Now I'm going to draw it on a dash, which means that the bromine should be placed on a wedge. Then I'm just going to fill in the remainder. Here I had the methyl on a dash. Now it obviously therefore has to go on a wedge. The hydrogen here is on a wedge. Now it has to go on a dash. Okay? And those are my two products of that reaction. Okay? So hopefully that makes sense. Let's do some more. Again, here's another alkene. I'm just going to draw the dotted line right through there. Okay? I'm doing chlorohydrin formation, so I'm going to add a chlorine, but I just have to remember the OH still goes on the more substituted side, which happens to be the left side in this case. So I'm going to put the OH there. I'm going to put it on a wedge, which means over here, the chlorine has to go on a dash. Then I'm going to fill in the remainder. Okay? The remainder is the methyl group here would therefore have to go on a dash, and then the hydrogen over here would go on a wedge. Okay, and that's one product. Okay, let's draw, in this case, it would be the enantiomer. Okay, so I'm going to keep everything there the same, but now the OH on the same position, I'm just going to draw it on a dash now. The chlorine, I'm obviously then going to draw on a wedge, okay, because it's anti. Then I'm going to fill in the remainder. The methyl group here was on a dash. Now I have to draw it on a wedge. Okay, and then the hydrogen here was on a wedge. Now I have to draw it on a dash. Okay, hopefully this repetition in these videos is helping. Okay, you understand this. Here I'm going to do this reaction. One thing I do have to remember, and I didn't cover this in the last video, but it is something that is important, and it's generally true of all these reactions. Remember that this is a benzene group right here, a phenyl group. It's aromatic. So when you do any of these reactions on that, it doesn't work. So the only thing I'm going to have to worry about is this double bond that's isolated from the benzene ring. I don't have to worry about it reacting with benzene. So I'm just going to apply what I've done before, draw the dotted line right through there. Let's do this. Let's pick everything on the bottom to remain the same. All right. So let's see. I'm going to just draw the benzene ring and keep everything. That was not good. And I'm going to keep everything here the same. Still not great, but we'll live with it. I'm going to chlorinate, and do a chlorohydrin formation. So that means the OH goes on the more substituted side. That just happens to be the left side. So I'm going to draw the OH over here, and then over here on the opposite side, on a dash, we put the chlorine. Okay. Then I'm going to fill in everything else, the remainder. This ethyl group, therefore, because this is on a wedge, the ethyl group has to be on a dash. And because the chlorine here is on a dash, the hydrogen, this one, has to be on a wedge. Okay. And again, I can go ahead and draw, again, what is the enantiomer. Okay. By the way, in these type of reactions for halohydrin formation, it is extremely common to get enantiomers. That's just something to watch out for. It's very common. In fact, almost in every case you do. Okay, unless it's a meso compound, which is also extremely rare. Okay. Again, OH is going to go to the more substituted side. That's this side, but I have to put it on a dash this time because I'm looking for the other product. And that means that chlorine over here would have to go on a wedge. Okay. Then I'm going to fill in everything else. The ethyl group here was on a dash. But because the OH is on a dash, I have to put the ethyl group on a wedge, okay? And because the chlorine's on a wedge here, the other hydrogen has to go on a dash. Notice in this case, again, this carbon right here is not chiral because, again, it has two of the same group, the two hydrogens. However, this carbon is chiral, okay? It's still chiral. And so this still is the enantiomer of this one. It's just there's only one chiral center. Okay? Now this one is a little bit of a trick question. Okay, I'm just going to go ahead and warn you, and the reason I do this is to illustrate a point. But let's go ahead and just do what we were doing. So I'm going to draw my dotted line right through there, and I mean, it really doesn't matter which side you pick the same. I guess I can pick the bottom again to stay the same in the plane. Okay, and I can even go ahead and, you know, draw at least part of that ring and all this. Here's the problem, though. How many substituents does the left side have? It has 1, 2. Okay. How many substituents does the right side have? 1, 2. Remember, the OH attacks the more substituted side. Okay. The problem is in terms of number of substituents, they're basically equal. Okay. They're both 2 substituents. So this is a case where this type of reaction is not really that useful. And here's why. Instead of getting, you know, 2 stereoisomers, like let's look at an example. Oops, let me draw this. Let's look at the 2 of the stereoisomers that we would get. Okay, so I'm just gonna do this really quickly, but just to illustrate the point. Let's go ahead and just put the OH right there. Okay, and then the bromine this time goes there, and then let's put again the OH here, and then the bromine there. And I'm just doing this really quickly just to illustrate the point, and then, okay, and then this goes on a wedge, and hopefully I'm not boring you, and then, okay, there you get that. Well, that is possible. This could happen, and in fact, if you did this reaction, it would, okay? You could get OH over here and bromine over there and so on and so forth. But the problem is there's just not really any selectivity in terms of does the OH add to this side or that side, because they're equally substituted. So not only do you get these two stereoisomers, in fact they are enantiomers of each other, okay, but you're also going to get some constitutional isomers. And let me show you why that is. Okay, let me just draw this real quick. So there actually is no preference that the OH would add to the green carbon, the left one. The OH could also add to the right carbon. What if we did that? Well, then I'd have OH over here, and then I could put the bromine on a dash there. And then I could put the OH on a dash again on the right side, and then put the bromine on a wedge on the left. And then I can fill in everything else. So then this methyl group on a wedge there, and this would be a dash there. And then again, methyl group on a dash, and then this is a wedge there. So what's the relationship between these two? If I was to say compound 1, 2, 3, and 4, well, between 1 and 2, those are stereoisomers, and 3 and 4 are stereoisomers of each other, but 1 and 2 are constitutional isomers of 3 and 4. When I say constitutional isomer, remember that implies they have exactly the same molecular formula, but the atoms are arranged differently, okay? Because the bromine and hydroxyl group are actually in different places. So this is a really important point. When you want to do halohydrin formation and you have an alkene and both carbons are equally substituted, that's not a good case where you want to do that. It's not a smart move to do halohydrin formation because you're going to get a mixture of constitutional isomers. And let's say, for example, maybe you wanted compound 2. Well, then you have 3 others, and if there were any other side products, but 3 main other products that you don't want, then you have to go and isolate 3 different ones. And since they all have approximately the same polarity, they're isomers of each other, same groups, it's going to be very difficult to isolate some of these. So you want to do it as efficiently as possible, and you'd theoretically not want to do it on an alkene where both carbons are equally substituted. Okay? So hopefully this video gave you a little bit of sense of the utility of halohydrin formation. And in the next video, we're going to explore some completely different reactions that we haven't seen before. See you in the next video. Make sure to like this video and subscribe to my channel. Thanks for watching.